Hello, everybody. Welcome to our web seminar today. Today, we're going to present operational transfer path analysis, which some people call OPA and some people call OTPA. And we're going to compare that to OPACS. And I'll talk about I'll show how to calculate operational path analysis, and I'll talk about some of the critiques we have of it. And then I'll introduce OPACS and give a demonstration of how to do OPACS in test lab. If you don't know me or you don't recognize my voice, my name is Kevin Grenier. I work in the customer services team in the United States. So first I'll have a couple slides on a transfer path analysis summary, and then we'll go into operational transfer path analysis, and I'll show how we can do OPA or OTPA inside test lab, and then we'll go and introduce test lab OPACS, and we'll give a demonstration on how we can calculate OPACS loads. And then I'll show some guidelines on how to get the best results. So we use this slide a lot when we talk about transfer path analysis, and we take a source transfer receiver approach. So on the left side, we have some sources, and I'm going to go through an automotive example today, but it could be an agricultural example, it could be a drill, anything that's causing some type of a force or some kind of a sound we can quantify through a volume velocity or volume acceleration. So we're going to have some type of structure-borne force or acoustic loading operating on our system. And that's going to be multiplied by the transfer functions between the source locations and different receivers. And the receivers in an automotive might be microphones inside a car at the passenger left and right ear. It could be an interaction point like a steering wheel or a seat track, or watching like a gear shifter wobble around or a mirror wobble around, for example. And we're going to study those transfer functions. And inside TPA, what we do is we multiply the forces by the structural A over F to get a partial acceleration, or we could multiply a Q by A over Q FRF to get the airborne contribution and sum those together to get the total response. And we can calculate that total response as the contributions of your structural and airborne sources and compare that to a measured target. And then we start looking at plots on the right where we're trying to rank the contributions from different paths to see what paths are contributing to the response the largest. And then we might want to go after those paths and try to improve them. Historically, we've used these techniques, direct measured loads. So we could actually cobble up a mount and put a load in there and measure the force directly. Or we use the mount stiffness method, F equals K delta X. If our sources are uncorrelated, we could do single path inversion. So we're basically inverting the FRFs around that source as a column of the FRF matrix. Or if the sources are coupled, we could do a matrix inversion. Or if the paths are coupled, we could do a full matrix inversion. These were the historical methods. Today, I'm going to talk about operational path analysis and OPACS, two different techniques. So if I want to show the concept for operational transfer path analysis, the idea is it's a very fast method. It only requires operational data of path references and targets. We don't need any frequency response functions. We use the transmissibility method, and we estimate the transmissibilities either from steady state or run up, run down. So basically, we're going to calculate an FRF, and because that FRF is response over response, we're going to call it a transmissibility function. And you can do it either at steady speeds, or we can do the averaging as we run up or run down to get an average transmissibility function. And as we show an example here, I would have a microphone in the car. On the passive side of my mounts, I would have accelerometers. I would calculate the transmissibility microphone divided by the accelerometer, multiply it by the same acceleration to predict that contribution. And we would do that for the airborne, and we would also do that for the structure-borne. So if I wanted to describe the airborne, I would have my microphone in the car, and I would have a microphone near the engine. I would calculate that transmissibility function as pressure over pressure. So that would actually be unitless. and I would multiply it by the operational pressure at the engine to get its partial contribution. And I could do that for several microphones inside the engine compartment. Or maybe I have a microphone near the exhaust and I want to get the contribution from the exhaust. So we're doing this contribution analysis using transmissibility functions multiplied by the acceleration or pressure right next to it. OPACS is a little bit different. OPACS is also a fast method. It requires operational data on active and the passive sides of the mount, depending on which technique you're using, and we need the noise transfer functions. So these would be the transfer functions from all of the paths to the targets. These use FRFs, so it's still a source transfer receiver approach, and we're going to solve for the forces using a parametric model that I described. So here in this example, we would have accelerometers at each of the path locations. So here I have an AP, which is my path. I get this transfer function to my target. That's your noise transfer function. And then if I have extra indicators, I can have extra indicators around those, and you also need those FRFs. And we'll talk about that when we do the OPACS method. But minimally what you need is you need the FRF from the passive side of the path to your targets. And then you need operational data on the passive side and possibly operational data on the active side. But the only FRF we need minimally is the path FRF. Compared to matrix inversion, where you need a much larger matrix of FRFs, here we just need the FRFs from the paths to the targets. So it's a lot quicker. And if you could do that reciprocally, if you can get this P over F by using a volume velocity source and getting your A over Q and converting that to P over F, this becomes a very, very quick FRF study. I could basically drive the vehicle into the lab, put a volume velocity source at the driver's ear, and get those FRFs reciprocally. So that's what it's talking about, this reciprocal transfer function. So differences between OPA and basic TPA. In transfer path analysis, it's a load-response relationship. In operational path analysis, it's a response-response relationship. It's not causal. The response may not be due to a force. It's a response-only study, whereas TPA is causal. The responses are due to a force. The noise transfer functions in TPA are system characteristics of your object. Transmissibilities are not a characteristic of the system. So for example, if I have an FRF, that FRF is related to whatever you're testing. If I look at a transmissibility function, it's going to be different at every single speed. So if I look at a transmissibility at 1,000 RPM, 3,000 RPM, 6,000 RPM, it's going to change. If I'm driving a different part of the road, that transmissibility function could change as well. And in traditional TPA, we can use the direct force method, the mount stiffness method, single path inversion, matrix inversion, or OPACS. So OPACS is just a different way to get a load in a traditional TPA study. Whereas OPA is really a different method using transmissibilities rather than structural FRFs. So in operational path analysis, it's all operational data. You would have microphones in the car for your targets, accelerometers wherever you have a target, like a steering wheel or a seat track. Then you put accelerometers on the passive sides of the mounts, and you get all of those transmissibilities. And then we multiply it by the accelerations at those same passive sides of the mounts to get the contributions. And we sum up those for the structural loads, and we sum those up for the airborne loads, and we get the total response. So a little bit different in that the targets are going to be a pressure. This is an airborne example. The paths are pressure. The FRFs are pressure over pressure, so they're actually unitless. And the operating data is pressure. And you can see when we set up the TPA model, we have targets and we have paths, but we don't need any indicators. And then here for operational data, I have an order. Operational data could be averaged frequency spectrums, averaged auto powers, they could be octaves, or they could be orders. And here I only have one order, but normally you have more than one. And then if I look at the FRF data, you can see it is unitless, pressure over pressure. If I look at the operating data, you can see it's Pascal. And then when I go to loads, I bring them in as direct loads. So basically, I just find the responses down at the bottom, highlight them, apply the load table, and move them up. And then our loads here are really pressure curves. So for structure board, here I have a target as pressure again. Could also have targets that were acceleration. My paths are again acceleration. My FRFs are either pressure over G or G over G. And here my operating data is acceleration on the passive sides. Bring them in as direct loads again. So instead of pressure, now I just bring my acceleration data up. And then now I have the contributions. And then the rest of the TPA looks like a traditional TPA. We can still use contribution to look at contribution. We can still look at path specific to look at path specific responses. And I can see here in this case, it looks like total contribution is a little bit lower than measured, and body 1Z is the largest contributing path. Right, so let's do a demo. So I'm going to bring over a target, and I'm going to bring over my paths here. And I wanted to show this because TPA is expecting forces by default. And if you're going to do operational path analysis, you have to switch that. So I'm going to change this to be acceleration. And then I can copy that all the way down. And then I need to find my operating data, and I found an order here. And then I go to my FRF selection, make sure I find it. So this is my target. Oh, I'm sorry, these are all of my path FRFs. Okay, so these are from the paths of the target. And then my operating data, I find that third order, and it's all in G. So these FRFs are pressure over G, and my operational data is G, and we're just going to multiply the two. When I go to TPA, and I bring them in as direct loads. So here are my loads. And now we just multiply those pressure over G loads by the G acceleration to get the contribution for each of these paths. So I go to TPA results. I tell it to update the display. And for third order, I can rate the different contributions at each one of these different speeds. And I can see around the speed, my total contribution is underpredicting a little bit, and body 1Z is the largest contributor. And then I can do the standard TPA plots if I want. And if I put this in DB, I can start to compare that total contribution to the measured. So green is my measured, red is the total contribution, and blue is the contribution to body 1Z path. And that's operational path analysis. The only trick is really when you go to build up the TPA model, you know you have to switch from force to acceleration. You don't need any indicators. Make sure you find the FRFs, and they either pressure over acceleration or acceleration over acceleration. So they'll show up as unitless. Bring in operational data as acceleration. Use them as direct loads. And then we just multiply these accelerations by the pressure over acceleration transmissibilities and get the partial contributions, and then sum them up. And then we don't suggest doing OPA. It works fine. I've actually helped 4 or 5 different customers calculate OPA results in test lab. So that's there if you want to use it. We suggest using OPACs, and I'll talk a little bit why in the next couple slides. So some of the criticisms we have of operational path analysis. So one criticism of operational path analysis is it uses transmissibility functions, and those aren't system characteristics of the structure, and they will change as your testing condition changes. So if you have issues at 20 miles an hour, 40 miles an hour, and 60 miles an hour, you really want to calculate those transmissibility functions at that speed. Or perhaps it's going to be different on different portions of the road. You might need to calculate them on different portions of the road. And then those could all be separate data cases you study. Operational path analysis is also sensitive to cross-coupling. So basically, if I have a high response at a particular response, so maybe I have path number 1 is moving a lot, that's going to show up as a large contributor, even if there's no force there. So we have an example where we have a high force at path 4 that causes a large dynamic response at point 1 due to the modal behavior of the structure. And that high response at path 1 leads to a large contribution in OPA. But if you do regular TPA, it doesn't, because the force at path 1 is actually very low, and the force is actually coming from path number 4. So if you were to use OPA, you would go after path 1 trying to solve the problem, and you'd waste a lot of time trying to change the stiffness or change the mount diameter of the wrong mount. So that's one of the risks. If you don't have cross-coupling, so if a force at one path doesn't cause a high response at another path, then OPA works fine. It's only when you have this strong cross-coupling. The total contribution is not a good check. So one of the things we do is I always compared my measured data to the total contribution of all paths. And it's easy to see if I'm missing paths or if maybe my paths have the wrong phase. In OPA, if you set up the test the right way, the total contribution always matches the measured. So think about it. If I have one run, and I put a microphone in the car, accelerometers at my path, calculate the transmissibilities, and multiply it by the accelerations at the paths from the same run, you're going to get exactly the same answer. So that's not a good check anymore when you use OPA. If a path is missing, you would never know. So same thing with the previous point. And in order to calculate these transmissibility functions, you need to be able to make sure that reference autopower matrix is invertible. And that means, A, the different paths should be uncorrelated. And if I have accelerometers on the passive sides of my mount and calculate transmissibilities, they're probably not uncorrelated. And that's going to cause issues in the transmissibility calculation. The other reason that the reference autopower matrix is difficult to invert is there would need to be enough singular values in the data such that we can do that inversion. So basically, if I was at a steady state condition and doing my averages, I may not have enough unique information at each frequency to have enough singular values to help with the inversion. You can help if you calculate the transmissibility as you're driving up or driving down and crossing through multiple orders. And if enough orders are excited at each speed, then that helps with that issue. But these are a couple of issues we personally have, Siemens has with the operational path analysis technique. We support it, just be a little bit careful. The other thing I'll mention here is through the years I've had people call me or email me and say, hey, if I calculate transmissibilities in test lab, and if I use one reference or two references or six references, they're different. And that's true. It's because those references are partially correlated. In a modal context, when we calculate a multiple input, multiple output FRF, the references, the forces have to be perfectly uncorrelated. Otherwise, that calculation falls apart. And that's what we see here as well, is that when you turn on multiple references, the transmissibilities will change. OPACS is another method. So this is a method we suggest you use. It's a fast method providing reliable path contribution. Differentiates from classical TPA in only the identification of the loads. So it's a new technique for calculating the loads. We basically solve a bunch of equations for a couple of unknowns and use that to calculate the load. So we have a soft mount model and we have a stiff mount model. I think they're called soft and indirect. So indirect would be for stiff mounts or acoustic loads, and soft mounts would be good for soft mounts. And basically, we're going to calculate force is equal to stiffness multiplied by the displacement. So we can subtract the accelerometer, the passive side from the active, divide by omega squared to convert to displacement, and multiply it by stiffness. And we're going to assume stiffness either through a single degree of freedom mount model, where we have three unknowns, mass, damping, and stiffness, or we assume a band estimator model, and we assume K is constant within a certain delta F. So perhaps you could assume K is constant across 30 Hertz or a 60 Hertz band. So here, in the single degree of freedom mount model, I have three unknowns for every path. Here I have one unknown for each band multiplied by however many bands you have. So if I have 10 frequency bands, I'm going to have 10 unknowns in the band estimator model, 3 unknowns in the single degree of freedom mount model. And then we can put bounds around mass, damping, and stiffness if you know about what they should be. We also have models where we can assume mass is 0 and assume stiffness is 0 and just solve for K. So we've got different types of mount models we can play with. For rigid connections, we're going to use the indirect method, and we only need the data on the passive side of the mount. And we calculate something, it's really not a stiffness, but it's an interim term that's used in order to estimate the force. Or we could use a band estimator model. For acoustic loads, we use a band estimator model. So this is the So the required data is we always suggest you collect the data on the active and passive side of the mount. So at the top is a acoustic, at the top is a structural load, and the bottom is an acoustic load. So if you're here for a structural load, we suggest always put triaxial accelerometers on the active and passive side of the mount. That way, if they're soft mount, we'll do the opaque soft mount method. If they're stiff mounts, we'll only use the passive side and we'll discard the active side and not use it. So we always suggest collecting the data on the active and passive side. That way, if it's soft, you can use both sides. If it's too stiff, we'll use just the passive side. And then you need the FRS from all of the paths to all of your targets. So those are required. Optionally, if you think you would help by having some extra formulas, we could have a couple of extra indicators spread around, and then you would need FRFs from the paths to the indicator. And it's not like matrix inversion where you need to have twice the number of indicators at paths to overdetermine. Here you're going to see you get a lot more equations by adding 1 or 2 extra indicators. So you don't need to overdetermine by a factor of 2 here. Just the way we set up the math, you'll see that with 1 extra indicator, you get a lot of extra equations to help to solve for the unknown. So I'll bring this up a couple slides. I mentioned a couple times about what data is required. But this is the first slide I show which data is required. Usually the targets, data on the active and passive sides of the mount, and the path FRFs are required. And then the other ones are optional. And these are some of the equations we start to set up. And this is talking about for all orders. So we can solve with operational data as orders, spectrums, autopowers, or octaves. So this is using an example of an order. And for every order, we can set up a bunch of equations where basically the response is due to the force multiplied by the contributions. And we can set these equations up for all of the targets, all of the indicators, using all of the inputs, and all the FRFs. So these are the equations here. So response is equal to the transfer function multiplied by the force, multiplied by the airborne transfer function multiplied by the airborne source. We need to know force, so we're looking for force, and we're going to solve a couple of unknowns in that force. So our unknowns are going to be either stiffness or stiffness, mass, and damping. And then we're going to know the responses at all of our targets and the responses at all of our indicators. And we're going to substitute these unknowns, estimate a force, calculate the partial contribution, and compare it to the actual measured targets and indicators, and use that to solve. And we're going to set up equations for all of the targets, all of the indicators, for all of the data cases, and all of the RPM increments. So in this example, I'm going to have 86 RPM increments on my order curve. That's basically the RPM steps. And I have 3 orders. So I'm going to have 86 times 3 number of equations multiplied by the number of targets used, multiplied by the number of indicators used. So you'll see that the number of equations can get very large, and you can add more targets or indicators to get more equations, or we can add more orders, or we can add more speed increments. So here's kind of an example of many equations due to the number of RPM steps or frequency lines. number of data cases, which is orders in this example. If it's steady case, you could have data cases at 20 miles an hour, 30 miles an hour, 40 miles an hour, and that would increase the number of equations as well, and the number of indicators. So hopefully your matrix is going to be well conditioned, or the equations are going to be well conditioned to solve. If not, we can limit the number of parameters. So we can do that by reducing some of the unknowns, by setting mass to 0 or damping to 0, or maybe just solving for k, or maybe just solving for k across certain frequency bands, or maybe you know some equations between mounts, and you can type in those equations, or maybe you know loads by some other technique, and we can use those a priori known loads. So if your math isn't well conditioned, and your condition number is high, we have some tools we can use to try to improve it by limiting the number of parameters or adding more equations. OPACS quality indicator, condition number must be low. And when we look at the total contribution compared to the measured data, it should be a good fit. If the condition number is too high, OPACS model is over-parameterized. You have a couple of options. I can simplify the model using prior known loads from another load technique, take larger frequency bands from my bandwise K model, if I'm using a bandwise stiffness model, change the mount model. I can set mount mass to 0 or damping to 0, for example, or we can, I spelled that wrong, we can provide bounds on mass, damping, and stiffness that you know, or we can go ahead and add a couple of extra indicators. And then you would need operational data at that indicator and the FRF from the paths to those indicators as well. And this is the same data set, but this was before I started editing it to make it look like an operational path analysis study. Okay, so let me add this to the input basket. Okay, so I have a microphone here. I have the same 15 paths. So I have 5 mounts with XYZ. And then I have the data on the passive side, body 1 to 8, and data on the active side, engine 1 to 8. And then I had to build up the mount table here. So here I have to build it up manually because I don't have any mount data. So basically I bring one side over, and then I map the other side to it. So body 1 matches engine 1, body 2 matches by engine 2, just like that. And then I have 3 orders here. I have 1/2 order, 1.5 order, and 1/3 order. I find my FRF data. It's found the FRFs from the paths to the targets. Actually, it's got paths to paths here, but I'm not going to use them. And then operational data, it's got all the operational data I need as well. So active and passive side. And if I go to loads, this needs an add-in. So in addition to TPA, you need the OPACS add-in. But technically, you don't even need transfer path analysis. If OPACS is the only technique you're using, you can just use OPACS. So if you want both, this is 98 tokens. If you just want OPACS, that's just 73 tokens. So if I only have OPACS, that's the only load technique I see. If you want to see the other techniques, then you need the transfer path analysis added. So I go to OPACS here, and then let me clear all my loads first. And first thing I like to check is I go to advanced options, and I check to see what's being used. And I'm going to do no reduction. So this is going to assume a single degree of freedom mount model. It's going to solve for mass, damping, and stiffness. And I've got the table set up here because I set the mount table up already on TPA model. Okay, so it's reading that. So you have to do this for a soft mount OPACS study. And if you had stiff mounts, you would do indirect loads, and you have to basically manually build up this table here. But I'm going to do soft mounts here. And now I'm just going to hit calculate and apply. It's done. And now you can see I've got one target being used. That's my microphone data. I've got 15 indicators. That's the passive side of my 15 mounts. It's using 48 total data used. So this is 15 indicators plus 1 target multiplied by 3 orders. So that's 48 multiplied by the number of RPM increments, which is 86. So that's how I get 4128 equations. And I have 45 unknowns. stiffness, damping, and mass for each of the 15 paths. I can see the condition number is really high. It's 21 million. If I wanted to look at these loads, I can look at these loads. Okay, and I can go ahead and immediately start looking at my TPA results. And I can look, looks like body 1Z is over predicting here. Oh, I gotta go to third order. And if I look at my path specific results, my body 1Z is the biggest contributor. And I can start to look at this in dB. So that's how we would look at the results. Okay, so I'm not too happy with this though. So I'm gonna go back to my TPA loads, and this condition number, I'm gonna try to get that closer to 100. So one thing I'm gonna try is, rather than no reduction at all, I'm going to reduce to a linear stiffness model. So I'm gonna set mass to 0 and just solve for damping and stiffness. So now my unknowns is 30 instead of 45. So that's improved. That went from 20 million or so down to 25,000. If I had good eyes, I could see how the load changed. And then I can see how the results change here as well. And I can look at these results. So that's one thing, but I'm still not down to 100. So I'm going to go back to advanced and then go to reduce to a constant stiffness model. So now it's just going to solve for K. Oh, I should point out too that the stiffness curve is being saved here. And if I look at the navigator in my TPA model, I can see my stiffness curves. So these are dynamic stiffness curves. So these are force over displacement. So one nice byproduct of OPACS is we give you the stiffness curves. So if you have trouble getting stiffness curves, this is a great way to get it for soft mounts. And then you could provide this to the CAE team, or I could also use this in a traditional mount stiffness method in traditional TPA. So these would be the stiffnesses used in a mount stiffness method TPA if you want. Okay, so now I'm going to go to this constant stiffness model. And now when I calculate this, now I'm going to see a flat line for stiffness here, which probably isn't very realistic. But holy cow, the condition number is great now. It went all the way down to 34. I don't trust those stiffness curves, but I can look at these results. And I can go to path specific here and look here for third order and look at those results. I'm actually getting fairly good results at this problem speed, but I personally don't think that stiffness is realistic. So what I'm going to do now is, rather than a constant K across the whole frequency range or the whole speed range, I'm going to use a band estimator model. And maybe I can assume K is constant across 30 Hertz. So now I can say, now my unknowns is 300. And I have 4128 equations to get those 300. Calculate and apply. So now I can see the stiffness curve is changing every 30 Hertz. Condition number is 164, so it's still a little high. If you want, you can start to look at those results again. If I come back to, I can look at the vector plot here. And if I go to 4800, which is my problem speed here. Okay, so you can see total and measured are pretty close. They're in the same quadrant and real close in amplitude. So we can still keep playing around. So maybe 30 is okay, but maybe I want to smooth the stiffness curve. So we can always do overlap. And you'll see now the unknowns will jump from 300 up to 540. So my condition number probably is going to go up a little bit more. Yep, see? So you have some options you can play with. And maybe you want to say, maybe I can assume it's constant across 60 Hertz. So that'll give me fewer unknowns, so down to 150. And then I can hit calculate and apply. Okay, so that's below 100. And then I can look at these results. Okay, so total's changing a little bit, but amplitude and phase is still fairly reasonable. I look at third order. Other things we can do is known mount relations. So let's say if I add rules, maybe it's nice to assume that the radial stiffness in each of my mounts is the same. So I can say, we do 4x. Oh, it's defined, this, I see, it's defined lower, that's why. X, y. So 1x, so I'm missing 3. So say 3x, let's see what it's doing. Okay. So for my 5 mounts, I'm going to assume the radial stiffnesses of all the mounts are the same, and that lowers the number of unknowns. So I can calculate and apply. Okay, so that dropped it down to 56. So that's one thing you can do, is we can apply these known mount relations to reduce the number of unknowns. Under equation balancing, we can rank the energy, or sorry, we could calculate the energy in each of the orders and then scale by that RMS energy to try to get all of the orders to have the same energy. And we don't suggest doing that because personally, if I have a dominant order, I want it to carry more weight in the calculations. But that's one thing we could do, is I could tell it to have equal order balancing. Then basically we're going to scale down the dominant order and scale up the less dominant orders. We don't suggest doing that, so that's why the default is no. If I had mixed units in each of my quantities, like sometimes you might have strain gauge responses as well as accelerometer responses. Those have very different scales. So we suggest calculating the balancing coefficients for the units and always using that. So that's the default here. And here I only have 1 unit, so it doesn't really matter. But if I had multiple units, you'd want to turn on, actually it's a default, make sure interquantity is on. You have to hit calculate so it calculates, and then it would start using those scales. Bounds, here I could apply bounds on mass, damping, and stiffness if you know about what they could be. And this would be another way to constrain the equations so that you get better results. We can also include just the targets. Okay, so now I'm going to use 1 target and no indicators. So now the equations really drop down. Okay, and condition number is about 2000. Or maybe you don't want to include the targets and you only want the indicators. So now I have 15 equations instead of 1 or 16, and I can try that. Okay, so you have choices. I can use all possible targets and indicators, all possible targets, all possible indicators, or define a mix. I can also solve stiffness case-specific or globally. So by default, it's globally, so we're calculating the same stiffness curve for all the data cases. If I say case-specific, I would get a stiffness curve, say, for half an order, 1.5 order, and third order. And maybe that makes sense to you if you're driving at different speeds, and at those speeds, you've got quite different load conditions, and maybe your stiffness of your mount acts differently. You could calculate case-specific stiffnesses there. But global is the default. You know, we could also limit the band here if you wanted to limit the range, and we can also extrapolate the FRF to the entire frequency range. Here I could use a priori known loads if you had loads from another method. And then down below, we can actually list the results. So if you have lots of orders, you can start to see these global correlation numbers. And if one of the orders is always really low correlation, perhaps you want to discard that order and not have it included in your calculations. Or maybe if one of your paths always has consistently poor correlation, maybe something's wrong with that data. You might want to go take a look at it. We also show you the mount stiffness parameters. So you can see the stiffness that was calculated. If I go back to no reduction here and calculate these results, and go back to the results, now I can start to see mass, damping, and stiffness. And then don't forget, back in the Navigator, we store all these. So we always have in the TPA model, under the OPEX K loads, we show those these stiffness curves. So these are my force over displacement stiffness curves. you want to put it in the millimeter, we can. And so this one is super, super, super high. So let's compare those to one of the other methods. So let's do the band estimator model, 60 hertz. Turn that off and calculate. Okay, and then we can compare it to these stiffness curves. So this was 83 to 18. Okay, so some of them are a little funky looking, but some are okay. Oh, that didn't be put it into millimeter. Okay, that's more realistic. I think that's it. So that was the software. Let me go back to the slides and see what else we wanted to cover. I talked about equation balancing. The default is not to do order balancing, but to do different unit balancing, and we suggest you use those defaults. Calculate the equal instance interquantity case coefficients to calculate these numbers. By default, they're 1. And then we don't do it automatically because people complained that when you entered OPACS, it took a long time because it was doing these calculations in the background. So we turn that off. And then if you want to do that, you have to come to this menu and click calculate. Structural paths, we always suggest you measure the active and passive side. That way, if you overlay them and they're similar, you would do a rigid connection. So we would do OPACS indirect. If they're well separated, we would do OPACS soft. So here's an example at the top where I'd want to do OPACS indirect, and at the bottom where I could do OPACS soft mount. I talked about the no mount relationships. Talked about the different advanced OPACS options. Talked about setting bounds on mass, stamping, and stiffness. Some advantages for OPACS over TPA mount stiffness. We don't need the mount data. So one of the problems with soft mounts in traditional TPA method is you have to give us a stiffness curve. And it has to be a dynamic stiffness curve, which is an FRF of force over displacement units. So you have to get that curve somehow. If that's an issue, we could use OPACS to get those mount curves. Then either use that in CAE or use that in a mount stiffness method TPA. Advantages of OPACS over inverse matrix inversion. It's a faster method. We don't need all of the FRFs from the paths to themselves unless you have a lot of cross-coupling going on. And then if you do have that cross-coupling, then you still want the paths from the FRFs in the paths to themselves. At some point, if you're going to do that, you probably may do a matrix inversion. So I think OPACS works best with soft mounts with data on the active and passive side. If you're going to do the indirect mount method for stiff mounts, by the time you get all the FRF data you need, you probably should do a matrix inversion anyway. Other advantage of the OPACS method is the traditional methods all solve frequency line by frequency line, and the loads can be kind of bumpy. So there's a lot of noise or variation in the loads. And here, because we can solve from the loads bandwise, the loads are much smoother in OPACS than matrix inversion, for example. Advantages over operational path analysis. OPACS uses a load response formulation. So it's using force-based transfer functions or volume velocity-based transfer functions. It doesn't have the limitations of OPA and gives reliable path contributions. Other advantage, the mount curves are a nice byproduct. And we can also solve for acoustic and structural loading at the same time. This is kind of a busy slide, but here I tried to show where you can collect the data. So you can collect all the data in Signature to get all the operational data, or we can process it in throughput processing. For the FRS, we can do impact testing or spectral testing or MEMO FRF testing. And the data that's required for all load methods, we always suggest you measure the targets and the passive sides of your mount. For the mount stiffness method, in the OPACS soft mount method, you should collect on the active side of the mounts. For matrix inversion and OPACS indirect, you want to measure some extra indicators. And you need the operational data for the indicators and the FRFs from the paths of those indicators as well. Required FRF data, all methods, we need the FRFs from the paths to the targets. The mount stiffness method and the OPAC soft, we don't need any extra FRFs. For matrix inversion and OPACs indirect, you need the FRFs from the paths to themselves to study cross-coupling, and you need the FRFs from the paths to the extra indicators. Thank you for your attention and thank you for attending.